We've learned that the eigenfunctions of a Hermitian operator, generally must be orthogonal. That is to say, if we were to take the integral over two of the eigenfunctions of a Hermitian operator, written like this, we should get one of two results. We should either get 0 if the two eigenfunctions are different, or 1 if they are the same. And this is assuming that they are normalized. All right, so can we show that this is true for harmonic oscillator states? Well, one of the things that we can tell right off the bat is that this particular combination will give us an integral that is 0 for harmonic oscillator states if m is odd and n is even, or vice versa. But what we don't know, for example, is would it also hold true if both m and n are either even or odd? Well, let's just try this out. I mean, we have nothing to lose. Let's put in this for n equals 0 and n equals 2 and see if we get the right result. So in other words, we're calculating, in essence, this entity. And I'm drawing it here in Dirac notation so that you can see how that looks. But what we're actually doing is we're evaluating this integral. We have 0 star x psi 2 of x dx. And if we write all this out, and I've written the general formula for the eigenfunctions of the harmonic oscillator up here, we're going to have two factors of this alpha over pi, so I'll bring that up front. So this is to the 1/2. We will have the integral 0 minus infinity to infinity. When n is equal to 0, this factor is just 1, so I'll have h0 of alpha x, which is just 1. I'll have e to the minus alpha squared x squared over 2 for the psi 0. For psi 2, I'll have 2 squared times 2 factorial, so that's a total of 1 over square root of 8. I'll have h of 2, which is 4 alpha squared x squared minus 2, and e to the minus alpha squared x squared over 2 dx. So this is the integral that we have to evaluate. Now a couple of things here. Square root of 8 is just 2 times the square root of 2, so I can divide that 2 into this to make that 2 alpha squared x squared minus 1. I'll bring the square root of 2 out here so that I'll end up with a factor of alpha over 2 pi to the 1/2. And then when I combine these two exponentials, that's the sum of the exponential powers, so since I have two of the same thing, it'll just end up being that thing times 2. So I'll have the integral from minus infinity to infinity. I'll have the polynomial part, which is 2 alpha squared x squared minus 1 times e to the minus alpha squared x squared, and this dx. Okay, now I can make my life a little simpler by looking stuff up in an integrals table, and I'll find that, for example, for a general Gaussian integral of the form e to the minus a squared x squared dx from minus infinity to infinity, the result will be the square root of pi divided by a. And similarly, if I were to do this integral with x to the 2n, so in other words an even power of x, e to the minus a squared x squared dx, what I would get in this case would be the following. I would have 1 times 3 times 5 up to 2n minus 1 divided by 2 to the n and then I would have the square root of pi divided by a raised to the 2n plus 1. All right, so we have a direct formula for calculating this. If n happens to equal 1, as it does in this case, we've got x squared. So if n is equal to 1, then this result will give us 1. 2 times 1 minus 1 is 2 times 1 minus 1 is 1, so I only go up to 1, divided by 2 raised to the 1. And then I've got square root of pi divided by 2n plus 1 is a3, or alpha cubed. So I'll have a factor of 1/2 alpha square root of pi over 2a cubed. In this case, it'll be alpha that's cubed. So now when I plug this into my integral for this overlap between the two eigenfunctions, I'll have a factor of alpha over 2 pi to the 1/2. I'll have an integral of 2 alpha squared of this integral, so I'll multiply this by 2 alpha squared, so I'll end up with an integral that is the square root of pi over alpha. Okay, for the other one, I just have the integral over alpha squared. Well, that's just the square root of pi over alpha. So we can see that these two things cancel out, and in fact, the result is 0 for this case. Now, if I were more confident, I guess, of my reasoning for these eigenstates and eigenfunctions, I would note in my Dirac notation that psi m of the Hamiltonian, psi n, would be equal to, because the Hamiltonian is a Hermitian operator, the reverse of this with the complex conjugate. So this is what it means to be a Hermitian operator. Okay, if this is true, well, I can operate the Hamiltonian on this function, which would give me a factor of e sub n, and leave me with the overlap between these two eigenfunctions. If I operated this Hamiltonian, then I'd get a factor of e sub m and star with this overlap. Okay, but this is just equal to, and since I know the eigenvalues are real, just equal to e sub m psi n. But when I combine this side and this side on the same side of the equation, I can write this as e sub m minus e sub n times this integral equal to 0. As long as e sub m and e sub n are not the same, so e sub m not equal to e sub n, and for the harmonic oscillator there's no degeneracies, so this is always true. If m does not equal to n, then that means that this part must be equal to 0. So indeed, I should see that all of the eigenfunctions of the harmonic oscillator are mutually orthogonal.